So now I'd like to invite up Kartik Singhal from Continuum. Today he'll be talking about Guppy, a Pythonic quantum classical programming environment.
Thank you, Josh. So yeah, before I start, a little intro about me. I work in the compiler team in the US side, which is more focused on hardware, but I get to collaborate with the UK team, who are the primary authors of the Guppy language. And I have a background in programming languages for quantum, and my motivation to do my PhD work was to really find ways to write reliable quantum software. So how can we ensure there are fewer and fewer bugs? So Guppy is close to my vision for that future for us. So before we get started, like, why Python then? Because Python is not really the most safe language in the world, right? But this is a survey result from Unitary Fund from 2023, and you can see that majority of our users are using Python. The only domain-specific quantum language in this list I see is Q#. I mean, I didn't get the whole list here, but it only has like 7% users. So we really need to see how we can utilize Python and its existing ecosystem. Just yesterday, Josh gave a keynote and he listed out why people really love Python. And we agree. I would take issue with just one thing: the dynamic nature may not be always very safe. So let's see how Guppy maybe helps us in that direction a little bit. So what is Guppy? It's a Python-like language. It's a high-level quantum programming language, and it looks like Python. And more than that, it's embedded into Python. So let me show you some basic examples. In Guppy, your gate applications look like function calls. So here is a definition of a RX gate using 3 other gates. So there is a so there's a header applied, then a RZ gate and a header. And you will notice that the gates are a little different here. You are passing in a qubit, but they return a qubit. So that's the discipline of linear typing. I'll talk about it a little bit more later. And you see that in a Python program, the Guppy portion of the program are distinguished by the decorator at Guppy. So moving on, we can just import in a normal Python program, Guppy like this, and then you can write your regular Python code. And the other important thing is that in each Guppy program, you have a entry point function. It's called main. And that's where you do your qubit allocations and return the final results. And what you can do after that is you can compile your Guppy program, and notice it's not dynamic anymore. It's actually doing compilation. You get a binary which you can then execute. And there are ways to execute it on a simulator, on our hardware, and potentially other targets. So this standalone executable can be shared with other people. There's a JSON output format we have. There are other serialization formats that are supported. And unlike approaches like Catalyst, which do tracing, in Guppy's case, we are parsing the ASD and doing compilation from scratch. So that gives us a lot more control over enforcing typing and other properties that we are interested in, nudging users into getting familiar with. So moving on, here's a more interesting example, which will show how Python's control flow is directly available in Guppy. So this is a repeat until success example, where we are trying to apply this V3 gate on the qubit Q. Gives this. And we use 2 ancilla gates, A and B, starting in the plus state. So in this case, in Guppy, we can start with a single qubit as input and then a bound on how many times we want to do an iteration. Then we can prepare the ancilla gates and apply the first CNOT gate and the adjoint to T. And then we can use the normal if conditional in Python to decide whether to repeat the first part of the RUS circuit or not. And if that goes through, we can apply the second part. And if it's success, we can use the break, which is the same as Python's break, and then just iterate if needed. And that's the whole program. It looks pretty concise, pretty readable, and we are able to use high-level control features. The most interesting part in Guppy, I think, especially the reason I like it a lot, is that we are able to enforce a lot of typing and safety. Because even in the quantum context, by the time you run the programs, it's kind of late. You don't want to use expensive quantum resources or even simulator resources. So while you are experimenting, if you get quick feedback, if your program has bugs, it's super helpful to make progress faster. So here's an example. In Python, this is a completely valid program, but you can see that the typing of X differs based on which branch was taken. So in Guppy, it's a compiler error. And this is just a very small example to demonstrate what Guppy can do. These features are maintained in any kind of conditioning, branching, looping. I don't want to go into too many examples, but point of the talk is here that Guppy's error messages are very nice, taking inspiration from modern languages like Rust. The other interesting feature is we use linear typing and it's enforced at compile time. So the idea for linear type is that resource like a qubit can be used exactly once at a time. You cannot freely discard it. You cannot freely copy it. That enforces the no cloning theorem. So here's one example of Guppy complaining when you create a qubit and try to apply a CNOT gate as the qubit both being the control and the target. So this red line indicates you will get an error there. Another case when you use a qubit, but do not use the output of that Hadamard gate. Like I described, the Hadamard gate has a input, which is a qubit, and an output, which is a qubit, just because it's a linear type. So this would be an error as well, because you need to use it and then manually discard it. Now, coming back to Python, another interesting feature is that you can continue using your Python libraries as usual. So let's say you want to create a graph state and use the NetworkX library. So you import your libraries the way you like, and then in a Guppy function, you can use the py constructor to convert a value from Python into Guppy value. So the way this works is that this code is run at compile time. That is, it is interpreted, the value of this graph is interpreted at Guppy's compile time, and then given to Guppy as a value. And there's a little restriction in that the type of the values you're importing should be compatible with the types that are available in Guppy. Speaking of what happens next, so this is the flow for compilation from Guppy. So the flow that we as a company are supporting for our next compiler architecture. So we use another intermediate representation that the UK team has developed called Hugger. So Guppy compiles into Hugger, and there's a new version of Ticket coming out called Ticket 2. Its input format is Hugger and the output format is Hugger. So it can do all kinds of optimizations that you're familiar with. And then it is given to the hardware compiler team. That is, it comes to us and we translate it down for lower level instructions. So Hugger stands for Hierarchical Unified Graph Representation. I won't talk about it today, but you should check it out. It's really cool. And that's the end.
Thank you, Kartik. It's great to see more examples of utilizing Python environments, but thinking about hybrid compilation and faster execution, especially taking into account control flow.